we can begin. So in today's video, we are going to discuss the assignments for week 5, not this year's assignment, the previous year's assignment. And in the process, we'll also look at some concepts. So at any point, if my screen is not visible or I'm not audible, then please let me know. So we have finished week 5, week 6 videos are out, and assignment 3 has been re-evaluated. So I will encourage all of you to look at your revised marks. So assignment 4 solutions are also released. So please fill the feedback form for week 5. Okay, so now let's go to the whiteboard. Right, so in this week, we have looked at videos that have surrounded over the topic of Treewidth. So maybe it is going to be a repetition for those of you who have watched all the videos, but it is necessary to define Treewidth. So I will do that, and then we'll look at the questions. So to understand Treewidth, let us first understand the tree decomposition. I mean, it's not the tree decomposition of a graph G, which consists of vertex set P and edge set E. So tree decomposition is defined as follows. So it is a tree T of bags X such that first, if UV is an edge in the graph, given graph, then U and V are together in some bag. And second, for all vertices in the graph, the bags containing a given vertex are connected in T. Okay. So basically, there is a graph, and you are converting that graph into a tree-like structure while ensuring that you have satisfied these two conditions. So we'll look at one simple example. Maybe we'll start with a tree. So a tree is already a tree, but even trees can be decomposed into trees. So let's take a tree. So let's example 1. Let me change the color of the ink. Okay, so let's say we have a tree. So we want to find a tree decomposition of this graph, which is itself a tree. So for every edge, we need to have a bag. So for every edge, so for this edge, AB edge, we have a bag. Bag means a set of vertices, basically. So for AB, we have a bag. For AC, we have a bag. For AT, we have a bag. And right, what else? CE, we have a bag. And CF, we have a bag. So 5 edges, corresponding to 5 edges, we have drawn 5 bags. Okay, so the first condition is satisfied, that for every edge, there is a bag in which the endpoints of the edge are together. Okay. The second thing is, for every vertex, the bags containing that vertex should be connected. So for A, so A is contained in which bags? This is one bag, this is one bag, this is one bag. They should be connected. So we'll draw edges so that these 3 bags are in a connected component in the tree decomposition. So similarly, how about B? So B is contained where? So B is here. Okay, so B has degree 1, so it is only contained here. So nothing to do. How about C? C is contained here, C is contained here. So these two should be connected. And okay, this C is here also. Right. How about D? So D is here. D is a leaf. Yes. Okay. So for D, there is only one bag. For E also, there is only one bag. And for F also, there is only one bag. Okay. So this looks like a valid tree decomposition of this tree.
But then A is appearing in three vectors. So how to make connections among them?
So you mean connection? So this is via connected via this. So this is a connected path. So
But
every
then,
bag is
yes,
reachable.
but AB is not connected to AD here. So if we try to
Connect.
connect AB and AD, this will result into a loop.
So when I say so, okay, so you are confused because the definition says that the bags containing P are connected means connected via not an edge, but a path is also fine. Connected means that there is a path between this bag and this bag. So and on that path, all the nodes are containing A. Okay.
Okay, so but I mean, so the tree decomposition of a graph is unique, or we can have different decompositions of a single graph?
It is not unique. There can be many different tree decompositions. So this is one of them.
Okay, all right, yeah, thanks.
Yes. So here the word connected means that there is a path between every bag containing a vertex. So for example, A is in this vertex, A is in this vertex. So there is a path connecting these two bags, and on that path, uh, each bag contains A. So this is not a formal definition. The formal definition was in the video. So for the purposes of our discussion, I have slightly uh, made it simpler. Okay. So the idea of connected is now clear, I believe. So connected doesn't mean that the bags have direct edge, just that there is a path between the bags, and on that path, all the bags contain that vertex.
Yes, and the decomposition is not unique.
Yes, decomposition is not unique. Correct. So let's take one more example. So for the sake of clarity, so let us say we have this graph A, B, C, D. So C are connected. There is G, G and D are connected. G and B are connected. H, F, E, F and C are connected. So this is a graph. It's not a tree. And we want to find one of the tree decompositions for this graph. Okay. So as I said that the tree decomposition is not unique. So there could be many tree decompositions, and any tree decomposition has to satisfy these two properties. So let me just draw one tree decomposition which I have worked out. Okay, right, so this is A. Okay, so here let us verify whether this is a valid tree decomposition or not. So for every edge in the original graph, so for every edge in the original graph, we need to see a bag where both the endpoints are existing. So let us say AB. So AB is in this bag. Okay. AD is also in this bag. BG in this bag. So DG in this bag, GH in this bag, FH in this bag, GE in this bag, EF in this bag, CF in this bag, CD in this bag, and DG. I don't know if we have seen it. So DG is already in this bag. So for this condition is satisfied that for every H, there is at least one bag where both the endpoints are contained.
So I have a query here that how is this possible that some of the bags are having 3 elements and some are having 2?
There is no restriction on how many elements will be there in one bag. So for example, if you take all the vertices of the graph into one bag, that is also a valid tree decomposition with only one node.
Okay, so like in this case, the degree of the vertex G is 4, so it could have been better that if you have included one bag having 4 elements, say H, B, D, and then E.
This what?
Because the degree of the vertex G is 4.
Yes.
So yeah, so therefore we could have included a bag having 4 elements, H, B, D, and then E. Wouldn't be better?
PH. Yeah, I mean, it makes sense. So yeah, so we are coming to answer your question because there are many ways in which tree decompositions can be formed. Some of the tree decompositions are desirable and some of the tree decompositions are not desirable. So your question is which one is better, which one is more desirable? So we'll be able to answer that question in a minute, but your
Okay,
point is valid.
okay, yeah, fine.
Yes. So right now, so whether this is a valid whether this is desirable or not is the next question. First, we will check whether this tree decomposition is valid or not. So we have already verified that this first condition is valid, is satisfied by this tree decomposition. And the second condition that we have to verify is that for every vertex in the original graph, the bags containing V are sort of in a connected component. And yes, so let us just verify for one vertex maybe. So A, so let us identify what are the bags that contain A. So this is one bag. This is one bag containing A. Right. So they are in a connected component. So there is an edge between them. So no, this is not very interesting. Let's look at B. So B is in this one, this bag, this bag, this bag. So again, if you look at the uh, these four bags, they also form a connected component. Okay, so it is possible to go from any of these bags to any other bag via these bags only, via the edges connecting these bags only. So others, for other vertices also we have to verify, but I hope that you will believe me that for the sake of time, we will just skip that. And this is a valid tree decomposition. Now the question that has been asked is a very prudent question, that why some kind of tree decomposition is desirable and which one is more desirable and which one is more not less desirable. Okay, so let us define the size of a bag is defined to be the number of vertices in the bag. For example, uh, so this bag has size 2, this bag has size 3, this bag has size 1, because there's only one vertex here, two vertex here, three vertex here. Okay, uh, fine. So now the width of a tree decomposition will define what is called the width of a tree decomposition is nothing but the maximum bag size minus 1. So what is the width of this tree decomposition?
2.
Correct. So the maximum bag size is 3. So 3 minus 1 is 2. In the previous one, the maximum bag size was 2. Therefore, 2 minus 1, tree width was 1. Okay. Okay. So now we are going to define the quantity which is of interest. That is the tree width of a graph. Tree width, or in short, we'll say TW of a graph. This is the least width of a tree decomposition for G. So there are many possible ways you can find a tree decomposition for a graph. As I said that if you consider all the vertices in a graph to be placed in one bag, then that is also valid tree decomposition. But the width of that decomposition will be n minus 1 if there are n vertices in the graph. And we will be interested in minimizing the width of a tree decomposition. Okay, so that is desirable. So we desire to have a tree decomposition where the width of the tree decomposition is minimized.
Okay. And what is the size of a bag here? Like, so this, I mean, do we consider the size of each bag individually, or
Yes.
okay, okay, all right.
So for this bag there is a size. For this bag there is another size. For this bag there is another size. But for the entire tree decomposition, the bag with the maximum number of elements minus 1 is the tree width of the entire decomposition, as is
Yes,
the definition.
yes, yes.
Okay. So now we have an idea that what kind of tree widths we are looking for. Okay, so uh, now we can move to the questions, or maybe I can give you one or two. So let's make some observations. So what is the tree width? What is the So now let me ask a question. So what is the tree width of a graph that contains at least one edge? Let me write down that question. So we can say what is the minimum tree width, or what is the lower bound? Let me write that way. So what is the lower bound on the tree width of a graph that contains at least one edge? It's non-empty.
1.
Yes. Can you explain why?
Because say if the graph is having one edge, then we require at least one bag containing two elements. So therefore the width will become 2. So therefore the tree width would be equals to 2 minus 1 1.
Yes, at least. Correct. So the lower bound is at least one, as is explained, the correct argument. So for tree, for any tree, that means a graph that does not contain a cycle, the tree width comes out to be 1. As we can see here, all the bags have width 2, I mean size 2. So therefore, the width of this tree decomposition is 2 minus 1. So for trees, we know that the tree width is 1. For cycles, we will see, and there are other things that we'll see, but yeah. So the first observation is that the tree width for any graph that contains at least one edge, any non-trivial graph, is 1. At least 1. So the lower bound is 1. Right. Now I think we can go to the questions. So I think the question is visible to you. So we have been given four statements and we have to decide which statements are true, which statements are false. So let us mark the statements A, B, C, D. So first statement says that graphs of tree with 10 cannot contain a clique on 11 vertices. Okay. So first I have to tell you what is the tree width of a clique. Or do you want to make any guesses that what is the tree width of Kn?
So Kn is a graph wherein the degree of every vertex is n or what?
Kn is a graph which has n vertices and each vertex is connected to every other vertex.
Okay, okay.
So it's a complete graph on n vertices.
Uh-huh.
Uh, yes.
Perfect. If we convert this such a graph into a tree, then every bag would be containing n minus one number of the elements. So therefore, the value of the tree width will come out to be n minus one, that is n minus 2. So if we have a tree width of equals to 10, then it can contain a clique of it can contain a clique of say clique of the 12 vertices, uh, because every vertex would be connected to every other vertex.
Okay. So tree width 10 will allow a clique of size 12. That's what you're saying?
Yes, yes,
So both A and B are false.
I think so.
Okay. So but I don't understand this argument that for Kn, uh, n minus 1 is the tree width. So that is n minus 2 is the tree width. So why do you think that every bag has n minus 1 vertices in it?
Because in Kn, every vertex is connected to n minus one number of the other vertices. So therefore, within a bag, it should contain not n minus 1, it should contain n number of the elements. So therefore, the
Correct.
value of the tree width will come out to be n minus 1. And if the tree width is n minus 1, then it can contain a clique of the size 11. However, it cannot contain a clique of the size 12.
That makes sense. That makes sense to me. So the first one is incorrect, that tree width 10 will not allow having a clique of size 11. That is incorrect. So even if clique size is 11, tree width can be one less, 10.
Yes,
But
yes,
if there is a clique of size 12, then immediately tree width will be 11 and not 10. So
yes.
this is true. That tree width is 10 means maximum clique size allowed is only 10 plus 1.
Hmm.
Okay, but yeah, so uh, I think your argument is correct. So let us visualize what you just said in a more concrete setting. So let us take the smallest clique possible. So let us take the smallest. Okay, smallest clique is only an edge. Let us take, I won't say smallest clique. Let us just take a triangle and see what is the tree width of a triangle. It is easy to visualize. So let us say that we have a graph which is a triangle, that is K3. So let us say there are three vertices A, B, and C. And one naive tree decomposition is to have all the vertices in the same bag, and that tree decomposition has width 3 minus 1 because bag contains three vertices 2. So the question is for K3, the tree width is 2, or we can do better. We can get smaller tree width. So according to your conjecture, like what you just said, for K3, n minus 1 is 3 minus 1, so it should be 2. So this is the best. This is the best we can do in terms of tree decomposition. But let us say that we can do better. Then by definition, for every edge, we need one bag. So for the edge AB, we have a bag. for the edge AC, we have a back. So here, what I'm trying to do is trying to see if smaller bags can still lead to a tree decomposition. Okay, so this is a valid this thing set of bags. But now the other condition is that for every vertex, the bags containing the vertices, yes, for every vertex, the bags containing the vertex should be connected. So therefore, the bag between the bags containing A, so AB and AC should have a connected path between them. So there is must be an edge this way. Similarly, for the bags containing B, there should be an edge. Similarly, for the bags connecting C, there should be an edge, but that we cannot draw because we want to make sure that the resulting structure is a tree structure. So therefore, we can see that having bag size equal to 2 does not work. So we can clearly visualize this in case of K3, and therefore the tree width of K3 cannot be brought down from 2 to 1. So 1 is not possible, right? So for K3, the tree width is actually 2, not 1, because the back size is 3. Right. Okay, so in general, the tree width of the complete graph on n vertices is n minus 1. And there is at least one bag in the tree decomposition which contains all the vertices of the clique. One such bag exists. And therefore, that bag size is n, and the width of this of that decomposition would be n minus 1. So we have been able to decide the first two statements, A and B. So now let's go to the statement C. So if a graph G has tree width K, then every subgraph S of G has tree width at most K.
So subgraph contains all the edges or all the vertices? What does it contain? If I take the subgraph of a graph G.
Subgraph means that you have the liberty to delete edges. So the edge set can be smaller. For
Okay,
example, yes. So let us say there is a graph and you deleted one or two edges, then that will sorry. So that will be
but the
called
vertices should remain the same, is it?
correct. That is not the definition of subgraph. So vertices can also be deleted. So there are two things. One is subgraph and induced subgraph. So when you say induced subgraph, so then we have a reference set of vertices. So we will say that induced subgraph on V dash, which is a subset of the set of vertices V. So when we say that we have an induced subgraph on V dash, which is a subset of the set of vertices, then that means that we are only allowed to pick vertices from V dash. Suppose these are the vertices from V dash. There were other vertices which we are not allowed to pick. Let us say these red ones were part of the original graph, but not in V dash. And edges will be between the vertices of V dash only. So if there is an edge between one blue and one red vertex, that edge will not be included in the induced subgraph. And
Okay,
when you say subgraph, you have the liberty to delete vertices as well as edges.
okay. So yeah. So now, what is the question? Can you show the question again, please?
This is the C part is the question.
Yes. Yes. So yeah. So clearly it is true, because if I take the subgraph of the graph G, then the tree width can never cross the value K. At the most, it could be K. Could be
Yes, that
less
is
than K.
correct. That is intuitively clear. So let us try to sort of make it slightly rigorous. Okay, so you have been given a graph G, and it is told that the tree width of this graph is k. So that means there is a tree decomposition. There is a way to decompose this graph such that uh, the bag containing the maximum number of elements in that tree decomposition has k plus 1 vertices. Okay. Now you are looking at a subgraph S of G. So some of the edges and vertices are deleted. But let me just verify it once what I just said, whether vertices can be deleted in a subgraph. Let's look at the definition once. A subgraph G of a graph is a graph G dash whose vertex set and edge set subsets of the graph G. In simple words, a graph is said to be a subgraph if it is a part of another graph. Yes. Okay. Just a second. So a graph, let me go to a subgraph of G is a graph having all its vertices and edges in G. Correct. If G1 is a subgraph of G, then G is a supergraph of G1. Let's see some images. Correct. So you can treat vertices and edges both as well. Okay, so now let's come back to the question. So maybe in the subgraph F, S, so S is a subgraph. So S is a subgraph of G. So some of the vertices and edges are deleted. Okay. So but still the same tree decomposition. The same tree decomposition will work for S as a tree decomposition. So what you will do is that you will simply remove the vertices which, so among the bags, so consider the tree decomposition for G. So let us say this is the tree decomposition for G. Okay. So maybe V is a vertex which belongs to S, but sorry, which does not belong to S, but it was there in the original graph. So that vertex V was probably in some of the bags. So you drop that vertex from those bags and rest of the things remain unchanged. So that by definition is a tree decomposition for S. And the bag size in that tree decomposition is not increasing. It can in fact decrease because if the maximum sized bag contains a vertex which was dropped, then the uh, width of the tree decomposition may decrease. So therefore, the tree width is at most k, it does not increase. Therefore, this one is true. Makes sense?
Yes.
Okay, so now let's move to the next one. So the only graphs of tree width 1 are forests. So we have seen that trees are graphs with tree width 1.
So just
So
now we
for
have seen, yeah, yeah. Please continue. Yeah.
yes, so forests are nothing but union of trees.
Mhm. So just now we have seen a graph having a single edge and its tree width was equals to 1. So therefore, it is not necessary that the only graphs of the tree width are forest. So even a graph having only one edge can have the tree width is equal to 1. So this statement is false.
So what is the definition of forest? I think we have to first see the definition. So what is a forest?
Collection of isolated collection of the trees.
Yes, collection of trees. So that means that it is not necessary that there is only one connected component. There may be several connected components, but each of the connected component is a tree inside.
Yes.
And
And
one single edge is also a tree.
yes, yes, right, right. So yeah, true, true. So yeah, yes, a single tree is a forest having just one tree. So therefore, this last option is correct. Yeah, true.
Yes. So what do we know? We know that for tree, the tree width is one. For a single edge also tree width is one because single edge is nothing but a tree. A tree is what is a tree? A tree is a graph without a cycle. So it's an acyclic graph. A tree is an acyclic graph that does not contain a cycle. So for a forest, for every individual component, we will draw a tree decomposition, and each of these tree decompositions will have back size at most 2, and therefore tree width will be 1. But the question is different. The question is, okay, so you argue, so far we have argued that for forest, the tree width is 1. The question is, are there any other graphs for which tree width is 1? Or is it the case that the only graphs of tree width 1 are forests? So that is the question. So whether there exist other graphs which are not forests, still the tree width is 1. So what does it mean? So it means that so a graph which is not a forest definitely contains a cycle. Okay. Yeah.
So if we have a cycle, then we require at least three edges, right? So if we require three edges, then as we saw last time, so we require a bag. Say
Yes.
if we go for if we have yes, so that can be done. That can be done. Just now we have seen in case of K3.
Yeah.
Uh, yes, here we had a bag having say three, so the tree width is equal to two. So the minimum number of the tree width is equal to 2 if we require a cycle here. So
Yes.
therefore, it can only happen in the case of the forest.
Exactly. So that is the way to argue. That is correct argument. So we have seen that, okay. So I was saying that, okay, K3 is one of the cliques. So it's a clique as well as it's a cycle. And for K3, we have seen that the tree width is minimum 2. There is no way to bring down this tree width to 1 because of this counterexample that we have produced. So similarly, if you have a larger cycle, let us say C5 or something like that, then also it is possible to prove that the back size cannot be less than 3. So I'll just draw something for you. So this is the tree decomposition for C5. Okay, I want to keep the question within our view. So let's draw C5. This is C5. Okay. And the tree decomposition looks something like this. So BC followed by, so I am quoting from one of the process. I have not verified it, but we'll verify it now. Okay, so let us verify. So what we have to verify that for every edge, there is one bag containing both the endpoints. So for AB, there is a bag. For AE, there is a bag. For DE, there is a bag. For CD, this one. For BC, this one. Okay. And what we want for every vertex, we want to see the bags are connected or not. For A, This is one bag, this is one bag, this is one bag, connected. For B, these two connected. For C, connected. I mean, everything is connected, but yeah, let's see. D, fine. D is connected. E, connected. Correct. So this is one of the tree decompositions, and here back size of 3 exists with Treewidth 2, and people have shown that for a cycle, getting the back size from 3 to 2 will be impossible. So if you have a cycle, therefore the graph is not a forest, then you cannot afford a tree width of 1. You have to increase. So this statement is true. Right? So I think we can move to the next one. So after the next one, we'll take a break because 2 hours becomes a bit tiring. So let's look at the next one. Okay, so this is third. Let's look at the second question. So second is this one. So this is a tricky question. It requires a bit of thought. So I'll let you think about it for a minute or so.
The question is not clearly visible. Can you scroll it down a bit? Thank you. Please visible.
So is it that the font is not clear?
The font is clear. The upper line was not clear. It is not. It is clear now. Yeah, it's clear now.
Okay. So I'll probably draw a diagram when you're reading this so that it becomes simpler, easier to sort of follow. Okay, so there is a graph. So there is a graph G. It has a set of vertices and edges, and there is a corresponding tree decomposition. So there are some bags. Okay. And the question says that, okay, so you have this graph and tree decomposition pair. So T be a node in the tree decomposition. So capital T is the tree decomposition, G is the graph, and you identify a node T, which is a bag. So T is a bag in the tree decomposition. Okay. So you have selected a bag T in the tree decomposition, and this bag contains a set of vertices. Let us say xt is the set of vertices in the bag T. So what you are doing is you are constructing a graph G minus xt. That means you are deleting from G the vertices in xt and the edges incident on the vertices in xt. So you are left with a reduced graph, so which is G minus xt. So let us call that graph G dash, or we need not call it G, this, let us call it G minus xt only. So maybe after the removal of these vertices xt, the vertices of G get divided into several connected components. So let's say several connected components are formed. There is no edge between one connected component and another. Such an edge is not there. Such an edge is not there. So this has happened after you have deleted the vertices of xt from G. Okay, so the question is, for every connected component C, of G minus xt. So let us give these connected components some name. So let us say this is C1, this is C2, this is C3, this is C4. I'm just taking four components for the sake of exposition. So for every connected component in this reduced graph, the vertices of C, the vertices in one of the connected components, are contained in bags of exactly one of the connected components of T minus T. So remember that once you remove that selected bag from the tree T, so we just remove it. So we get rid of this bag and the edges incident to it. So then the tree itself is also divided into several connected components. So here only two. Here there are only two connected components, but there could be more connected components. So the question is, all these vertices which are in one connected component of the original graph will lie exactly one connected component of the tree decomposition after T has been removed. So that is true or false. That is the question. If you don't understand the question, then I can repeat what I said.
So can you summarize this question once more?
All right.
So here you have drawn C1, C2, C3, and C4. So these are after the removal of the XT or before the removal of the
After the
XT?
removal, after the removal. So these are in. So as this question is saying, for every connect component C of G minus xt. So after xt is removed from G, these are the
Mhm,
connected components. So one of them is C1, the other is C3, C2, C3, like that.
mhm.
So similarly, when T was removed from the tree, that so the tree is a connected graph, but once you delete one node from the tree, it becomes disconnected. So if let us say there was one more bag here, then this edge will also get deleted because it is incident on T. And then we'll have three connected components. This is one connected component, this is one connected component, and this is another connected component in the tree decomposition. So you are looking at connected components in the tree decomposition after removal of T, and you're also looking at the connected components in the original graph after removal of xt. So the claim is, for every vertex in one connected component in the reduced graph, all the vertices within this connected component are lying in only one connected component in the corresponding tree decomposition also.
Yes. So if we consider that a vertex in a connected component C is contained there in say two components of the
Yes,
corresponding tree. So yeah, let us consider say A, and A is at two places. So since A is an element of a connected component, so these two vertices should be connected via some route, right?
correct.
So, but then this cannot be the case, and this cannot be the case. Why so? Because A could have been belong to say the T which has been removed,
Exactly.
or A could have been the case otherwise, right? So all the paths which are going through T and which have been removed. So yeah, so I think that the statement is true. Or do I need to consider any other possibility that may exist? So the other possibility could be that if it belongs to say this vertex which is already connected to A, but then it lies within the same component. So therefore, this is true.
Correct. So your argument is correct, except I will add one more sentence. So in a tree, because it is a tree, there is a unique path from every node to every other node. And if
Yes.
yes, so if you consider for contradiction that in a component C, there is a vertex A, which is in a bag on this side of T and also in a bag on this side of T, then the path connecting this bag to this bag must go via T, because this is a unique path. And because it goes via this node T, it must also contain A by the definition of tree decomposition, that if there is A here, there is A here, there is A here.
Yes.
Okay, so therefore, but A is already, because if A is here and A is already deleted, then A cannot surface in any of these components. A was deleted. A is, if A is here, then A is in XT, but A we already deleted. So A was somewhere here. And therefore, we
Yes.
have come at a contradiction. And therefore, this statement is true that all the vertices in one component is also present in only one connected component in that corresponding tree decomposition.
So how difficult it is to translate this entire discussion in a nice mathematical form, in a nice proof? How difficult this entire process is?
Can you rephrase what you asked? I'm not sure. It is not very
Yeah.
precise.
So whatever we discussed to reach to this conclusion that this is true, and if I want to convert this entire discussion into a nice mathematical proof, then how difficult this entire process is. Wherein I start writing the proof like that, let G be a graph and this is G dash, and after removal this thing, and I prove it by the contradiction. So usually, how difficult this process?
So usually the difficulty lies in identifying the mode of attack. For example, here we identified that the best way to approach this problem would be via contradiction. We can try to prove something via contradiction.
Mhm.
So here we have been able to, let us say, make an assumption which is to the contrary and then arrived at a contradiction. So if this contradiction argument did not work, then we will probably draw a counter example. So this proof via contradiction is allowing us to conclude that this statement is true. If on the other hand this statement were false, then we have to give a counter example. So there the difficulty will rise in designing that counter example, which in most cases are non-trivial.
Right. Yeah.
Yes. So for example, if this were not true, then you would say that okay, here I show you a graph and here I show a 3D composition and here I delete one bag and corresponding vertices in the original graph, and then I show you one vertex inside a component that is spread across two components on the other side.
Yes.
And in general, finding counterexamples are not trivial. Uh, so that much I can tell. Okay, so I think that there are three other questions for today. So I will just let you stare at question number 3, and we will take a small break of 5 minutes.
Yes.
I'll let you look at both the questions. Okay, so we'll resume after 5 minutes.
Yeah, the very first line of the question is not visible. Actually, you'll have to scroll it bit down. Yeah, it's okay now. Thanks.
So I think that you are not, you have zoomed in. Okay, so there is a way to zoom in and zoom out. If you're on a tablet, you can just use two fingers. And
So
if
I'm
you're on your,
I'm trying to zoom in. I'm using desktop and I'm not well versed with Microsoft Team. So whenever
okay,
I try to zoom in, the entire content goes away. So so
okay,
therefore, yeah,
okay. So you have to play around with it.
yeah.
All right. Okay. Okay, we can restart. Okay, so you are able to see the screen, right?
Yes, yes.
Okay, so in this question we have a graph and it has certain attributes and we want to find some bounds on the tree width of this graph, and we have to decide which of the following bounds are true. Let us mark these bounds A, B, C, D, E. So what does the first attribute say? So the graph has a clique on 7 vertices. So we have already seen that the tree width of so in one of the questions we have seen that if S is a subgraph of G, then the tree width of S is at most the tree width of G.
Yes.
Yes. So another way of writing this is that tree width of G is at least I'm just swapping sides. So the tree width of the original graph is at least the tree width of the subgraph. So here we know that G is a graph which has a subgraph which is a clique on 7 vertices. So there is a K7 which is a subgraph in G. So that means that the tree width of our graph is at least the tree width of K7. And we know that tree width of K7 is how much? N minus
7
1.
minus 6. Yeah.
Yes. So basically this one is immediately true. But how about this? So let us mark this as true. So what can we say about the second one? Can the tree width grow even larger? So we have to look at the next attribute that this graph has. So the graph has a subgraph, which is the graph has a complete bipartite subgraph with 9 vertices in one partition and 6 is in another. So it has a subgraph. So let us say 9 vertices in this direction. I mean, okay, so I have to make a larger circle.
And how is this possible that the graph is a complete bipartite graph and as well as is having a click of the size 7?
No, no. The graph is very large. A small portion of that graph is a K7. Another side, maybe somewhere in another direction, the graph has another subgraph, which is a complete bipartite graph, where one partition has 9 vertices and the another partition has uh, 6 vertices.
But then it says that the we are considering a single connected graph G and which has got the following three properties. So
Okay, let us try to see. So let us draw if such a graph can exist, we'll try to draw. So let me then make it bigger, just we'll draw it below. So I will just move things around. Okay, so first let us draw a K7. So a K7 is a set of 7 vertices. Okay, so let us name them. So V1, V2, V3, V4, V5, V6, V7. Okay, so I'm not drawing all the edges, but make an assumption that every vertex in this K7 is connected to every other vertex. So all the other edges that I have not drawn are still there. Okay, so this is a K7.
yes.
And then there is another part of the graph which has a complete bipartite subgraph on 9 vertices in one partition. So let us call them x1, x3, x4, x5. Okay, just let me push this things up so that we can see everything in one page. X6, x7, x8, and x9. And it has 6 other vertices on the other side. Okay, so now this is a complete bipartite graph. That means every x vertex is connected to every y vertex because it's a complete bipartite graph. So I'm not going to draw everything, but the idea is you connect every x vertex to every y vertex. So these edges are all there. And so let's say I'm not drawing everything, but you can understand what I'm about to draw. I'm, I'm referring to. Okay, so this is another thing. Another thing is this graph has a cycle on 42 vertices. So there is one more cycle. So let's say this is cycle. There are 42 vertices on the cycle. So this describes 3 subgraphs in this graph. So maybe the graph has other vertices, other edges also. They are connected in some way. So that is a statement. That is the description of the graph. Do you understand?
Yes. So now in case of the complete bipartite graph, since every vertex is connected to every other vertex, so say for x1, I am having say 6, x1 is connected to 6 other
Yes,
vertices.
correct.
So to whomsoever this vertex x is connected, all those components should become the part of the same bag. So
Right.
so so therefore this would be having then 6 plus 1 7. So therefore the every bag here would be containing say 7 uh, 7 number of the
Vertices. 7
yes
vertices. Yes,
ISIS.
exactly.
So therefore the value of the tree width came out to be 6.
Correct.
And
Correct.
but then I mean the question is that can we increase this value or not? So
Yes.
if we consider the third case wherein there is a cycle of the 42, then even we just need to store say 3 vertices within a bag because every vertex is connected to 2 other vertices. So therefore, the value of the tree width came out to be 2. So we cannot increase the value of the tree width beyond 6. So I think all other options are incorrect.
So how about looking at it this way? So consider this part of the bipartite graph which has 6 vertices. Now every yi is connected to 9 x sub j's. Okay.
Yes, yes. So yeah, that's true. That's true. So then each bag would be containing say 10 number of the vertices. So
Okay.
therefore the value of the tree width came out to be 9. And now we can increase the value of the 6 beyond, increase its
Okay.
value, but then the option B would be correct.
All right. So you are taking back the previous answer.
Yes, so I think that TW is greater than or equals to 6, it is true, but then TW would also be greater than or equals to 9, that is another possibility.
Okay. So the thing is, okay, so I confused you. My apologies. Uh, but the idea is just looking at how many neighbors one vertex has. Will not be able to decide the largest back size in a 3D composition. So because now I pointed out to you that okay, there are vertices which have larger degree, then you have changed your answer. So there is no direct correspondence between the tree width, that is the largest back size in a tree decomposition, and the degree of a vertex. Okay, so for example, in this case, I will draw a tree decomposition of this part only of this complete bipartite graph where one partition has 9 vertices and the other partition has 6 vertices. And it will turn out to be that every bag has 7 vertices. So tree width is 6 in spite of the fact that there are vertices with a degree 9.
Yes, this
So
is also right because it is not necessary that we need to consider. We need to consider. Yeah, I mean the decomposition is not unique, and even a bag having 7 number of the vertices would suffice.
yes, so it is not related to the degree as such. So let us draw this. So let's do one thing. Let's call this entire set as a Y set. So Y is the union of this 6 Y vertices. So the tree decomposition is the following. So you consider so Y uh, as one bag. So this bag contains 6 vertices. So there are 9 other bags. So there are 9 other bags. So first bag is Y union X1. So this is one bag, and this is a child of this. There's another bag Y union X2. So 7 vertices each. So similarly, so we'll take one X from each of these 9 X's and we'll have 9 children. So the last child of Y would be Y union X9. This is another bag. Now, is this a valid tree decomposition? So other bags are there. How many bags? So in total, there are 10 bags in
Yes.
this tree decomposition. Okay, now we have to verify two things. So first, whether for every edge, there is a bag containing both the endpoints. So the edges are between X and Y and not between within Y's and within X's. So this bag contains all the pairs where X1 is present in one side and all other Y's are also there. So for all the edges such that X1 is an endpoint is taken care of by this bag. Similarly, all the edges where X2 is an endpoint are taken care of by this bag and so on. So therefore all the edges are taken care of. So for all the edges, there is a bag which contains both the endpoints. Okay. Is that correct?
Yes. Yes.
Yes. So what is the next thing to verify? That for every vertex, the bags containing that vertex must form a connected component. So how about x1? So x1 is contained here. So for every x, there is only one vertex. So there is nothing to be worried about connectedness. But for y values, let us say y1. So y1 is here as well as here as well as here everywhere. So that's a connected. So the entire tree itself is the connected components for every y. So even
Yes.
for y2, we have a connected component because y2 is all the y's are appearing in all the bags. So we have a connected component because itself is a tree. So therefore, this is a valid tree decomposition. And the maximum bag size is size of y plus 1. So the tree width is 7 minus 1, 6. So there is a lemma, there is a result which says that for a complete bipartite graph where one partition, let us say, so complete bipartite graph, let us say we'll call it G is equal to V1 union V2. So one partition is set of vertices V1, the other partition is set of vertices V2, and some edges in the sense all edges, all possible edges in the bipartite graph because it's a complete bipartite graph. The tree width of G is the minimum of the cardinalities of V1, V2. So in this case, the cardinality of one set is 9 and the cardinality of the other set is 6. The minimum of 9 and 6 is 6. So therefore, the tree width we have found is 6. Okay, and this is the realization of the tree width decomposition, tree decomposition.
Yes, it's clear.
Okay. So therefore, uh, out of these three features that this graph contains, this feature gives us a lower bound of 6 on the tree width. This feature gives us a lower bound of 6 on the tree width, and this feature gives us a lower bound of 2 because it's a cycle. How large the cycle does not matter. Cycle has a tree width of 2. So only this option is correct, and this all other options are incorrect. And so we cannot
Yes.
say
But then
anything
in this
beyond this.
question, nowhere they have mentioned about the subgraph kind of the thing. If we see the problem formulation, then they have only mentioned the connected components probably, and they have not used the term subgraph.
So when it says that G has a clique on 7 vertices, it means to say that there are 7 vertices in G such that each pair of them has an edge between them. So you can consider this as equivalent to saying that G has a subgraph which is a K7.
Okay, okay, all right.
So all other statements turns out to be false. Okay, so let's move to the next one. Okay, so this one is comparatively straightforward. You're able to see the statements, I believe.
No, you'll have to scroll it down a bit. Yes, it's okay now. Uh, which of the following statements are true?
So you have a graph G and you pick one vertex from the graph. You delete that vertex from the graph as well as the incident edges on that chosen vertex. So now you
Mhm.
have a graph G minus V. So what is the relationship between the tree width of the original graph and the reduced graph? Is it equality?
So it is not necessary that if we take the example of the K3, and if I remove one
Yes,
vertex from it, then only a single edge would be remaining, and it will make the tree width is equal to 1. And however, the original tree width was equals to 2. So therefore, this statement is not correct.
correct. Yes. So that is the right way to. So basically, here you have argued that this statement is false. And to
Hmm.
argue that this statement is false, you have come up with a counterexample. So,
Yes.
so what I said a few minutes ago, that if you want to prove something false, you have to draw. One of the approaches is to uh, construct a counterexample, and that's exactly what you have done.
Yes.
So yeah, we
And
have already discussed these two things. Uh, Fine. So let's move to the next one. So is it true that once you delete a vertex, the tree width of the reduced instance is at least the tree width of the original instance minus 1? So that means deleting a vertex cannot drastically reduce the tree width. It will reduce the tree width by at most 1. That is the claim of the statement.
so, yeah, but then I cannot think of any. Yeah. So if I remove a vertex from a graph and say if that vertex is the central vertex and central vertex, and if I remove all the vertices from it, and
So
if I and
what do you mean by central vertex? Are you talking about a star?
yes, yes,
So you're talking about a star and the center of the star.
center of the star. So if I remove this V from here, then like in this case, the tree width is equal to 1. But then why don't we connect all other vertices also? Let it be a nice wheel kind of a thing.
Okay.
Yes. So now every vertex is connected to 1, 2, 3. So yeah, and 1, 2, 3, 4, 5, 6. So it could be. Mhm. Uh, uh, but if I remove this one from here, so then it will be 1. Yes. So like in this case, the tree width is equal to say 2. Uh, because
So
if
we.
I
Mhm.
for this graph, uh, say I consider the value of the tree width is equal to 2. And if I remove the central vertex from here, then the value of the tree width will came out to be 1, and which follows this inequality.
No,
Uh,
why? For a cycle, we already argued that the tree width is 2, irrespective of the size of the cycle. So once you
yes.
delete V, we are left with a cycle. So let us say that we delete one of these edges. So you don't want a cycle. Let us say that we don't have this edge.
Uh-huh,
Now what you are saying makes sense. So we have a path,
uh-huh.
uh, but yeah. So in the path, tree width will
But then
become.
here we have removed an edge and not any vertex. But it says that G minus B, the tree width of the G minus B. So we'll have to remove a vertex only.
Yes, yes, that is fine. No. So what you initially said, you said that once you delete, so let us say you have a wheel as
Uh,
before. So initially you said that okay, we have a wheel and we have a central vertex, and
uh,
we delete the center of the wheel. So once you
yes.
delete the center of the wheel, you are left with a cycle on 7 vertices.
Yes. So, but then the tree width would be equals to 2 and the tree width remain the same. So therefore, this statement is not
Makes
true.
sense.
Yeah, this statement is not true. It is not necessary that if I remove a vertex from the graph, then at the most I would be reducing the tree width by an amount of 1. Uh,
So your tree width is decreasing by more than 1. Tree width is becoming 2 to 0. No.
no, it is not becoming 2 to 0, but then it remained the same. Earlier also it
Yes.
was 2, and this time also it is equals to 2.
So the statement is as such not invalidated.
The statement is not contradicting as such. Yes, it would be greater than or equals to this thing. Yeah. So this is not the. I mean, this example does not contradict the this
Correct.
statement.
This is not a counter example as such.
Yes.
Okay, so the other way to look at it is to try to see if we can prove it true. And if we have to prove it true, then we can try via contradiction our same old friend. So let us say that we'll just push these things to the right side. So there is an easy way to look at it. Before I go to the contradictions part, let us just look at it plainly. So you have this initial graph, whatever that graph is, you know that there is a 3D composition of that graph. So there are bags, and these bags are connected with edges such that the two conditions of tree decomposition are satisfied. Now you have dropped one vertex from this graph. So now you have minus one vertex. So that vertex V, if let us say that there is, and just for the sake of argument, let us say that there is a bag which is the largest bag. It contains the maximum number of vertices. So that bag is sort of witness to the tree width of this graph. Now, if V is not contained in this bag, so if V is not here, so this does not contain V. So what happens to the tree decomposition of this graph? Uh, the tree width does not change. Yes,
Yes. If it is not the bag having the maximum number of the elements, and if you remove this vertex B from it, the value of the TW is not going to change. However, if this is the bag which is containing the maximum number of the elements, and if you remove this vertex B from here, the value of the TW would be less than, or maybe could be less than or equals to the TW of the original thing minus one. So which
exactly.
makes this inequality true.
Correct.
Because
So
two cases may arise. Either this bag is containing the maximum number of the vertices alone, or there could be many more bags which are having the same number of, and which in fact are again containing the maximum number of the elements.
makes sense. So this biggest bag need not be unique. There could be multiple biggest bags,
Yes,
largest
yes,
bags. So so the worst case, the tree width can drop by one because we are dropping one vertex. So the back size can drop by one in the worst case, but not more.
yes, yes.
So the statement says that okay, I delete one vertex, tree width drops by at most one. That's what the statement is saying. Either it does not
Yes.
drop or it drops at most by one. So that is one way to look at it. Okay, so I think we are at 7:30, so we have one more question that is very interesting question. So you can also try to prove this via contradiction. So if you want to approach it via contradiction, then you will say that okay, that I have deleted a graph and the tree width has decreased by 2. So there is a bag which was containing so many vertices, and now that bag doesn't contain, or the largest bag doesn't contain even minus 1 that size. I mean, the largest bag size has dropped down by 2, and then you arrive at a contradiction. So you make an assumption to the contrary and you arrive at a contradiction. So that is another way of approaching it. But for the sake of time, I will not go towards that because I'll solve one more question today. Okay, so let's move to the next one. So what is this next statement? So it says that for any edge UV in the graph, if you drop that edge, if you delete that edge from the graph, then the tree width does not change. It remains the same.
This is false because quite possible that in a bag having the maximum number of the elements, quite possible that UV, both elements might be there. So if I remove that n age, so clearly that UV, I mean the value of the TW will change, will get reduced by one. If it is the bag containing the maximum number of the elements.
Yes, another way is this counterexample that you have constructed for falsifying the first statement. This also acts as a counterexample in this case.
Yes, yes, yes.
So here one edge was dropped from the triangle and we got a single edge. The tree width for the single edge is only 1, whereas the tree width for the triangle was 2. So therefore the uh, deletion of the edge has resulted in a drop in the tree width. So this statement cannot be true because of this counterexample.
Yes.
So now we are asking that okay, if edge
So
and it
yes.
drops, yeah,
So if you consider this argument along with the option B, so therefore this has to be true. Whatever argument I gave just now regarding the falseness of this option C, that if this bag is containing the maximum number of the elements and if you remove and UV both are there, and because of the connectivity in between U and V, so if I remove UV from here, then at the most this TW can drop by an amount of 1. So this is
okay.
true.
I go with that. Okay. So yeah, so next question is slightly tricky. I think in today's discussion, the most interesting and trickiest question will be this, and we'll spend 20-25 minutes on this. So I'll let you read the question. It's slightly technical. I mean, slightly involved. All the questions are technical, sorry. Okay, so I have to define what is a caudal graph. So let me first define what is a caudal graph. So you're able to see the question, right?
Yes, yes, visible.
Okay. Okay, so a graph is called caudal. A graph is called caudal if any cycle of length 4 or more has a chord. Yeah, so that's it. So what is a chord? Let's define what is a chord. So chord is an edge connecting non-adjacent edges in the cycle. Okay, so how about so is this a caudal graph?
So do we have a cycle of the length greater than or equals to 4 here? 1, 2, 3, 4, and 5 years. And chord in the sense that we should find an edge containing non-adjacent edges in the cycle.
No,
So
this is connecting. This is connecting.
connecting. So only one edge, or we would be requiring many edges, like here 1, 2. I mean, this chord part is not clear. That what constitute a chord?
Okay.
Single
So
edge.
correct. So you have a so in the graph, let us say let us say there is a graph and I'm looking at a part of the graph and I identify 4 vertices in the graph which form a cycle. 4 or 5 is also allowed, but at least 4. 5, 6 is allowed, but not a triangle. And if you identify such a cycle, then on this cycle, every non-adjacent vertex should have an edge. That is a chord. A chord is defined as an edge connecting non-adjacent edges in the cycle. So if G is chordal, then every cycle of length at least 4 has a chord. Right. So for example, if you have a C5 and you say, okay, there is no, these two are not, let us say, I name it 1, 2, 3, 4, 5. So here, say 4 and 2 are non-adjacent. So it cannot be lying unconnected. So there must be an edge between 4 and 2. But that does not make this graph caudal because again, there is a cycle. This is a cycle on 4 vertices, 1, 2, 4, 5, and 2 and 5 are non-adjacent. So once you draw this edge between 2 and 5, now this has become caudal. So
Yes.
basically you are triangulating.
Okay. So now in this original graph, uh, uh, this is not a caudal graph, because if I consider a cycle of the length 4 or greater, right? So I have a cycle of the length 4 is 1, 2, 3, and then 6. And now 2 and 6 are not adjacent. However, they are not connected. So
2 and 3 are adjacent. You mean 1
2
and
and
3?
2 and 6.
Right. That is also true. So I'll
So
draw an edge between 2 and 6. So now we can call this graph caudal.
no, this is yes. After connecting 2 and 6.
Yes.
it becomes caudal. Yeah, because the triangulation has been done for everywhere rather. Yes.
Yes. Okay. So now we are on the same page that what is a caudal graph, and now we can read the question. So caudal graph is one in which all cycles on four or more vertices
We'll
have
have
a chord.
to, can you slightly scroll it down a bit? Thank you. Yes. So yeah.
So, so you are on a desktop, right?
Yes.
So you don't have a touchpad, you have a mouse.
Yes.
Okay. So I think what you have to do, just a second.
So there is an option of plus here, but whenever I press it, the entire content goes either
So
towards the
you
left or
you
towards the right.
you press minus. Is there a minus option?
But if I press minus, it becomes the entire thing is visible, but then the entire thing becomes so small that it is difficult for me to read on the screen.
Oh, okay. Okay, fine. So now, anyway, so whatever is the most convenient way, the way we were going, so just get back to that configuration.
Yes,
Uh,
it is okay now.
okay, right. So let us read the question. So a chordal graph is one in which all cycles on four or more vertices have a chord, as we have seen in this picture. So let G be a simple chordal graph. So simple means that there are no multiple edges between two vertices or no self loops.
Hmm.
So the first statement is all induced cycles in G have exactly three vertices. So induced cycle means uh, you have chosen a set of vertices, and uh, so the definition of induced graph is you choose a set of vertices from the vertex set, and all the edges among these chosen vertices have to be taken. So if it turns out that you have an induced cycle, that means you have, let us say, chosen four vertices, and it turns out that the four edges forming the cycle are present in the graph. So the question is saying all induced cycles in G have exactly three vertices. That means it cannot happen that you have a cycle on four vertices in an induced cycle. Uh,
No, no, this is not necessary. So just now we have seen, I mean, in this example only we saw a cycle of the length 5 also and the cycle of the length 4 also. So it is not necessary that the induced cycle in G uh, would always have three vertices.
no, so it's a chordal graph. So I'll just try to draw. So let us say for the sake of contradiction, okay, so just tell me whenever you're not able to see, okay?
Yes, yes,
So I'm moving slightly up. You're still able to see
yes, yes,
now.
yes.
This is more I can go up. So
But
are you
that's it.
able to?
That's it. Yeah, this is the limit. Yeah.
All right. So what I will do is I will push these things down, and I will just have both the question and the discussion within your view. Okay, so now I'm going to. Okay, so now you're able to see the question as well as this empty space at the bottom.
Yes, yes.
Okay, so now let us say for the sake of contradiction that there is an induced cycle. So means induced means what? So induced subgraph means if you say that, okay, if we make a statement that induced subgraph on a subset S, so S is a subset of the vertex set, that means that you have picked some vertices, and in the original graph, whatever edges were there among these vertices, you have drawn all of them. So that kind of a subgraph is called an induced subgraph. Okay.
Yes.
Now suppose for a contradiction, for the sake of contradiction, that there existed an induced cycle on four vertices. That there exists an induced subgraph or cycle on 4 vertices, more than 3. So that means you have a vertex 1, you have a vertex 2, you have a vertex 3 and 4, and they form a cycle. So remember that all the edges you have to take, all the edges in the original graph within this, among these 4 vertices you have taken, and it turns out that you have a 4 cycle. But you already know that this is a caudal graph and you are looking at an induced subgraph of the caudal graph. So this immediately violates the caudal nature of the graph because this two non-adjacent vertices do not have an edge.
Yes.
So therefore, we have arrived at a contradiction. Oh, so I want to apologize for something. So this is the symbol for contradiction. So in the previous video, I was writing like this. So this means if and only if, and this is the symbol for contradiction.
Okay. And moreover, there has to be an edge in between 1 and 4 also, is it? Because this
No,
graph,
one of them.
yes, one of them. One of them
So
or
once, as soon as you have drawn this edge, so
Mhm.
the existence of the 4 cycle without chord is destroyed. So that 4 cycle is destroyed. You have triangulated that 4 cycle. So either this diagonal or this other diagonal is sufficient to destroy the existence of this 4 cycle. So basically, we want to destroy all larger cycles.
Yes, yes, right, true.
Okay,
So
so it turns out that all induced cycles in G are basically triangles. So this is true.
mhm.
Okay. So the next one says an induced cycle in G may have 3 or more vertices. I mean, more vertices is not possible. That is what we have just proved.
This is false. This is false.
Immediately false. So if G is connected, then every minimal cut. So I have to define what is a cut. Induces click. Okay, let me define a cut. Okay, so this is a slightly involved argument. So let me first uh, copy this statement and it will take few minutes to discuss this. Okay, so I'll just copy the statement. It says that if G is connected, so G is a caudal graph as well as it is connected, then every minimal cut in G is a clique. I mean, induces a clique. So let's just write this. So you're able to see this part of the uh, board.
Yes, yes, I can see it.
All right. So so let me first define what is a cut. So a cut is a set of a subset of the vertices. So cut is a subset of the vertex set. B such that removal of, let us say, cut S. So let us say we denote the cut by S. So S is a set of vertices which is a subset of the vertex set. And if you remove this cut, then the graph becomes disconnected. Removal of S from G makes G disconnected. So that is the meaning of a cut. So for example, let us say this is a graph and okay, this is what I should do is Maybe this edge I can remove. Yes. So now if you remove this vertex, then you are left with two connected components. So one is this vertex and the other is these three. And there is no edge between these two components. So the graph has become disconnected.
Yes, so okay. So now in this case, which vertices are the part of the cut? The one which is in the pink color or
Yes.
okay, okay. Yes, makes sense.
Okay. So this is the definition of a cut. And a minimal cut is a cut which from which you cannot delete a vertex. So let me do one thing. So let me just I'll just take one more example. Let me think of one more example where there are two vertices in a cut. Uh, so let us say this is a graph. Okay, so I will do one thing. So now I'll use a different color. So in this graph, these two vertices, if you remove, then you are disconnecting the graph.
Yes.
Okay. So if you say that, okay, I don't want to remove these two vertices, I'll remove only one of them. You're saying that, okay, maybe remove this one. Then it is not a cut.
Yes, because it is not making the graph disconnected.
Yes. So these two vertices, let us call them V1 and V2. So V1, V2 is a minimal cut. That means any subset of V1, V2 is not a cut.
Yes, so and this collection has, I mean, should form a bridge-like structure. So if I remove it, things are going to be disconnected, is it?
It depends. For a caudal graph, that is not the case. That is the question. That for a caudal graph, this minimal cut, in fact, is a click. So there would be an edge in the caudal graph. That is the question. So G is caudal. So we already have that G is caudal as well as connected.
Mm-hmm.
So we want to prove that every minimal cut of this graph induces a click. Okay.
Mm-hmm.
So
So my point is that if the graph is a caudal graph, so all edges, I mean, there is connectivity in between the non-adjacent vertices. There is a connectivity in between all non-adjacent vertices, and moreover, this graph is connected. So we should be able to make a move from a vertex to any other vertex in the graph. So don't you think that this is possible only if the graph is a click only? The entire graph is a click.
so you're
Uh,
saying that all caudal graphs are cliques.
so my point is that all connected caudal graphs are the clicks.
So how about this graph?
So is this connected? Am I able to make a move from this vertex to this vertex, any other vertex? Yes, I can make a move, and yeah, and then this is not a click. Yeah, this is not necessary. Yeah, fine.
So all caudal graphs are not cliques, but all caudal graphs avoid large cycles. So there is, of course, many edges. So the density of edges is not small because we do not have large cycles. We do not have large holes. So to say, cycles are also called holes.
Mhm.
So yeah, so we have very few minutes left. So I'll just go to the proof of this. So this will take 5 minutes. It's a nice proof. So we'll go by, so we want to prove that this is true. Okay, so we'll go by contradiction, our favorite tool.
Yes.
So you can see the question as well as the empty space below.
Yes. Yes, I can see.
Okay. So suppose that for the sake of contradiction, suppose that S, which is a subset of the vertex set, is a minimal cut, but it's not a clique. But S does not induce a clique. Okay. Okay. So now, so what does S look like? So S is separator. It is a cut. So let us say this is S, and it is some vertices. And it's not a clique. So some edges are there, but not all the edges between every pair of vertices are there. Okay. But once you remove this, the graph becomes disconnected. That means components are formed. So these are connected components, but within two connected components, there are no edges. So there is no edge like from this connected component to this connected component, or this connected component. These edges are not there. Okay. So I'll remove this. So for this, for the sake of easiness, let us say that removal of this set of vertices S leads to only two connected components. That is how the graph is disconnected. Let us say C1 and C2. Okay. Just only for the ease of the same. So now we will use the fact that S is a minimal cut. So because S is a minimal cut, therefore every vertex in S has one edge going to a vertex in component 1 and at least one edge going to a vertex in component 2. So that is a property of a minimal cut. So do you understand? I'll just write it down. So every vertex in S must have a neighbor in C1, component C1 as well as component C2. Because if not, then let us say this edge was not there, then this cut can be reduced. So you can take this vertex inside this component C1 and then removal of the rest of the vertices of S is also a valid cut. Did that make sense?
Yes, because S is a minimal cut. So
So any subset of S cannot be a cut. But here we have exhibited a situation where one vertex from S has been taken out and it is included in the other component C1, and still the rest of the vertices in S is able to disconnect the component C1 and C2. Because see,
correct,
this
correct, correct.
vertex,
Yeah,
this
understandable.
vertex is connected on this side only. Yeah. So removal of, so this vertex is not essentially contributing towards disconnecting these two parts.
Yes. So therefore this cut is not the minimal one.
Yes. So it proves that every vertex in the minimal cut S must have a neighbor in both the components C1 and C2.
Yes.
So I will draw two edges. So now consider, so this is true for every vertex in S. Okay, now because S is not a clique, so by assumption, S is not inducing a clique, but it is a minimal cut. So therefore, there is at least one pair of vertices in S which don't have an edge in between them. So let us mark these two. So everything else I'm going to delete. So there is at least one pair of vertices in S, let us mark them 1 and 2. They don't have an edge between them because S is not a clique. Okay.
Mm-hmm.
So now by this property, there is one edge from 1 to this side, one edge from 1 to this side. Similarly, there is one edge from 2 to this side and one edge from 2 to this side. Okay.
Mm-hmm. Mm-hmm. Yes.
Now let us say that so this is V1, let us say, and this is V2. V1 could be equal to V2. There is V1 may be equal to V2 is allowed. And this I am writing because of this property P, that every vertex in S must have a neighbor in both the components. So let us say that the neighbor of 1 in this component 2 is V3 and the neighbor of 2 in this component C2 is V4. So but V3 is equal to V4 is also allowed. Then observe that we have a cycle of length at least 4. So what is that cycle? So this is, remember that V3 and V4 are either same, or because it's a connected component, there is a unique path. Not unique, there is a path between V3 and V4. So either way, this entire thing is a cycle of length at least 4, which
Yes.
contradicts the fact that we are dealing with a caudal graph.
Right.
So
Because
hence,
in that case, it can only have a maximum of length 3.
exactly. But even if V1 is equal to V2 and V3 is equal to V4, then also we'll have 1, 2, 3, 4 sized cycle.
Yes.
So therefore, this statement is true because we have arrived at a contradiction, and hence, if G is a connected caudal graph, then every minimal cut in G induces a clique. So such pair of vertices 1 and 2, which are non-adjacent in S, cannot exist.
Right.
All right, so we are just in time. So we have been able to deal with 3 parts of this question. So this turns out to be true. And I will let you stare at the rest of the 3 statements. In fact, I will upload it to YouTube also. So I will encourage you to try to solve this 3 other questions. Okay.
So
Yeah,
if
go ahead.
yeah, if G is not a clique, then there exist subgraphs G1 and G2 of G such that G is equal to G1 union G2 and G1 intersection G2 is a clique. All right. So if G is not a clique, then there exist subgraphs of the G1 and G2 of the G such that okay, so either the union of both the graphs would be, or the intersection of. So what could be the meaning of the intersection of the two graphs?
Uh, so the question is the following, that G is a caudal graph, but it is not a
Mm-hmm.
clique. So a clique
Mm-hmm.
is definitely a caudal graph because in a clique there cannot exist a 4 cycle. A clique is always triangulated, isn't it?
Mm-hmm.
I mean, not triangulated. For example, if you have a 4 click, so you have one more edge. I mean, there are no 4 cycles for sure. So suppose G is a caudal graph as well as it is not a clique. Then there exist subgraphs of G, G1 and G2, such that G1 union G2 is G. Okay, so basically you have divided the graph into 2 parts, G1 and G2. So this one is G1 and this one is G2. But it may happen that G1 and G2 have some intersection. So maybe it is like this. So this is G1 and this is G2. So there is an intersection of G1 and G2, and that part is a clique. So you have to show the existence of subgraphs G1 and G2 such that this property holds that okay, G1 union G2 is the graph, but G1 intersection G2 is a clique. So basically you have to use this fact that if you find a minimal cut in G, let me just do this. I'll just give you a hint. Okay, so the idea is the following, that you have a minimal cut. Yes, suppose you find a minimal cut in the graph. So minimal cut will, disconnect the graph into certain connected components. So let us say 4 connected components. I'm just saying 4, but it can be any number. Then what you do is you form a graph G1 by taking all connected components except 1 and S. So this is G1. So G1 is, let us say, we move, so I'll just write. So let us say G1 is the connected component C1, the connected component C2, union the connected component C3, union the minimal cut. So it is this portion of the graph. And the other connected component is the minimal cut and C4. So that is G2. C4 union that minimal cut. So what is the intersection of G1 and G2? So G1 is
intersection
this.
is S only.
Only S. So that is a clique. So you have a solution. So taken together, it forms the entire graph. And you have already argued that the minimal cut is a clique. And here you have a construction where the intersection of G1 and G2 is that minimal cut, which is by previous statement is a clique. So
yes,
so
this
this
is true.
statement is true. Yes.
If S is such that the S index is a clique in G and TB is a tree decomposition of the G, then there exists a node T such that S is contained in the beta of T, right? So then there exists a node T such that S is contained in the beta of T. So what this beta of T here is that there exists a node T, the subtree rooted
So
at the node T.
beta is denoting the bags. So you have a graph and you have a tree decomposition T of the graph. So beta is the set of bags in the tree decomposition. So beta of T means for a node T in the tree, the bag contains which all vertices?
Okay, so if S induces a click in G, so every vertex is connected to every other vertex, and so since every vertex is connected to every other vertex, so this should be true. This should be true. This should be true because S is inducing a click in G. So every vertex is connected to every other vertex. So just now, I mean, in the beginning of the session, we saw that the beta would be of the length say n minus 1, and so
Exactly.
therefore this is true. S is contained
Exactly.
in
Yes, that is right. So
uh,
because there is a clique,
uh,
so S is inducing a clique, and
uh,
oh sorry, I have used that pen. Just a second. So S is a subset and it induces a clique. Okay, and T beta is a tree decomposition of G. Then one of the nodes will contain all the vertices of S because S itself is a clique, and for a clique in the beginning we have seen that one of the bags must contain all the vertices of the clique.
yes, yes. And the last one is that G has a tree decomposition such that every bag in the tree induces a click. So G has a decomposition such that every bag in the tree induces a click. Every bag in the tree induces a click. This is not necessary that every bag induces a click. So what does it mean? That all the vertices which are there. So if there are three components A, B, C, so there A is connected to B, and A is connect. Yes, this is true. This is true, I think.
Yes, this is true, but the argument is slightly trickier.
Mm-hmm.
So it basically would follow from what we have seen here that you you start with a minimal cut. So let's
Mm-hmm.
look at this diagram only.
Mm-hmm.
So the minimal cut is guaranteed to be a click,
Mm-hmm.
and then you have these components, and
Mm-hmm.
on these components again recursively you can find minimum cuts. So those minimum cuts, because of the fact that the graph is a connected caudal graph and these components are also connected caudal graphs, would again be cliques. And then you would be able to finally get down to a, so you recursively compute cliques, minimal cuts and other connected components. And then within the other connected components, again you find minimal cuts. Finally, your base case will be you get down to one single edge, or you get down to one vertex. So that is again a clique in one vertex or two vertex. And then this you have to argue that this procedure will lead to a tree decomposition. And each bag in the tree decomposition is nothing but these vertices on the minimal cuts, this SS. So this is a slightly uh, bigger, lengthier argument. But essentially, the hint is this. So you start with a minimal cut in the graph, and recursively for every component, you find the minimal cuts.
Yeah.
So I will mark it true.
Yes. So what will be covered in the next session then?
So in the next session, so the plan is for me, my job is to discuss the problems for every week. So week 5 is completed. So we're about to start week 6. So the
Okay.
expectation is the learners will watch the week 6 videos. Then we solve some problems based on week 6. In fact, we'll solve exactly those problems which were part of the assignment in the last offering of this course.
Okay. Okay. Yeah. Thank you so very much. And you are already late by 11 minutes.
Oh, it is fine. So I'm very glad that you dragged it 10 more minutes.
Yeah.
So yeah,
I thoroughly enjoyed this session. I learned a lot. Thank you so very much. Yeah.
okay, okay. So just let me stop the recording. Uh,
Yes.
uh, just a second.